Sorry about that.
You got a warning window came up. Oh, it just went away.
Should be okay then.
Are we streaming now?
Looks like it. Yeah, it's all good now.
Okay. Good morning. My name is Tanishka. Welcome to Orchard Park Secondary School, home of the FRC Team 2056. If you have any questions throughout the day, please feel free to ask me. I would like to introduce our speaker, Michael J. Martin, presenting the importance of radio frequency communication in robotics.
Thank you. Good morning. My name's Michael, and today we're going to be talking about radio frequencies, or RF as we call it. And this technology is used everywhere. It's vitally important for any autonomous vehicle. They cannot work without communicating. Everybody thinks they're independent, but the truth is far from that in reality in the industries. And I'll share with you some examples of how we use autonomous vehicles. The robots that I work with are quite a bit different than what you do. Mine are in the neighborhood of 800,000 pounds, and compared to yours, which you can pick up. Mine are 40 feet high and 60 feet long. I'll show you some pictures of them in a bit. And again, we have robots in every part of the industry. My background, I'm a graduate from Orchard Park here in Stoney Creek, and I grew up here and went to school here for 4 years, and then went on to various university pursuits. And when I left Orchard Park, I moved to Japan and studied at the Tokyo Institute of Technology, and I studied film and photography. And that gave me a great background for understanding radio frequency, because a camera lens, is very similar in physics to a satellite or microwave antenna. So the same physics, just different frequency. I've been a lifelong student. I continue to do learning all the time. And I have 8 degrees today, and I have 4 master's degrees. And with those different educational pursuits, I marry it all together to do designs for very large scale systems. One system I did, my first AI system, was in 1996, a long time ago. And it was on the space shuttle, STS-56 mission. We put a camera on the space shuttle to analyze the citrus crop in the state of Florida. So we've been doing AI for a very long time, and also integrating RF into these communication systems. What I'll say is, here's a short video. One of my first big AI projects, which involved a lot of RF and a lot of communication. And it was for the neonatal ward, which is premature babies being born at the Hospital for Sick Children in Toronto. And in this case, the infant was in an incubator with 16 different machines around the incubator connected to the infant. And we're pulling about 300 points of data per second off the baby. And every piece of machinery came from a different company, and none of them spoke to each other. None of them had the same protocols. So we had to strip the datagrams apart. We used MQTT as a protocol and harmonized them all through MQTT. And I don't know if you know about MQTT, but it's a way, or a common protocol. It's used in Facebook, for instance, so you probably use it all the time if you use Facebook. But here's a short video on that. Let me just start it here. Maybe.
There's a baby generating data in a neonatal ward. Every heartbeat, every breath, every anomaly, from over 1,000 pieces of unique information per second, helping doctors find new ways to detect life-threatening infections up to 24 hours sooner. On a smarter planet, analyze the data and you can predict what will happen faster. So you can do what they're doing in Toronto and build a smarter hospital. That's
So that'll give you a little idea. It said, I told you we did 300 connections. It said 1,000 pieces of data because what we did was we integrated data together and we derived data. So we created new data from the source data that we had. We also had legacy data, history data, and there's different forms of data that we used. So there was real-time data, telemetry coming from the infant. There was legacy data that was from thousands of previous babies that we knew the trends and patterns of. And then there was external data where we were getting inputs from external sources that may be related or unrelated to the baby. And we use these three pieces, external data, real-time data, and legacy data. We use that all the time in every robotic system we use, whether it be a greenhouse I've done automated on, or a mining equipment or whatever. The external data might be weather information. It might be all kinds of different parameters that have influence on the outcome of whatever platform we're working on. So the first question is, what is modulation? And here's an engineering definition of modulation. And it's pretty complicated. It might be a lot of gobbledygook to you. So I've got an analogy I'll share with you to help you understand modulation. If you understand some of the basics, then it's really easy. I use a lot of analogies because with RF, you can't use your senses. You can't touch it, you can't feel it, you can't hear it. And so you don't know that it exists. Most people are visual learners. So by using parallels and analogies, we can understand things easier. So let me share one with you right now. I call this the Kool-Aid analogy. You all have had Kool-Aid, you've drank it before, and you understand that you get a package of Kool-Aid, and when you rip it open, you can smell the flavor, you can sense what's going on, but it's a powdery form. It's not anything. Let's call that, it's the basic form of the signal, okay? So that's the Kool-Aid, it's a crystal. And if I told you I have a pipe and the pipe's 1 kilometer long, and I want you to run that Kool-Aid through the pipe, you won't be able to do it because when you pour it, all the crystals will just fall out and nothing will go in there in the pipe. So what we do is we take the Kool-Aid and we'll mix it, throw it into a bucket, okay? Into the bucket, we'll add water, and water and the Kool-Aid get mixed together. And then we'll take a pump and we'll pump the water out of the bucket through the pipe. And at the other end, we'll put the water, the Kool-Aid, into another bucket. Then we'll put a fire underneath the bucket and we'll evaporate the water. Now, if you can imagine what we have in the second bucket now, it's the same Kool-Aid, but now it's still soggy. It still hasn't separated from all the water perfectly. It's not as bright or orangey or red, whatever it was when it went in. And that it has deteriorated through the journey, through the pipe. And some of it may have stuck to the pipe or gone somewhere else that we didn't, some of it may have evaporated with the water. So what's all that mean? What it means is that the Kool-Aid is the baseband signal. We call it baseband, it's the basic signal. And the bucket is like a buffer. So we load the baseband signal into a buffer. Then we mix it with a radio frequency carrier, which is like the water. And then from that, we pump it. And the pump is an amplifier or an antennas or whatever fiber optic amplifier, whatever we use, whatever kind. There are different kinds, but we can pump it through the pipe. The pipe may be free space, meaning microwaves over the air or microwaves going to a satellite like Starlink or something, okay? And then it could be fiber optics or it could be all kinds of different media that we would use to transport the signal. At the other end, the second bucket is also a buffer. And so we demodulate the signal there and we separate the RF carrier away from the baseband signal, okay? And that is basically describing analog transmission to you. Because in analog, it deteriorates over the journey. It gets worse and worse. So if we did this process 4 or 5 times, after the 5th time, the Kool-Aid would almost be transparent. It wouldn't be any color at all. It would be lost in the process. But when we do digital, we do it differently. we do the same process. We mix the baseband signal. In this case, we mix ones and zeros. And the ones and zeros are formulated into bytes and datagrams, and then we send them along. But what they give us is a recipe for Kool-Aid. So we send the recipe through. It's very easy to send the recipe through. It's not like sending the Kool-Aid through, which was very hard. Now at the other end, we can reproduce the Kool-Aid because we have the recipe. We know how to make it. So at the other end, we have a perfect version of Kool-Aid because we made it brand new at the other end, on the second end. So that's effectively what we're doing with digital. We're sending ones and zeros. We're sending a recipe, a formula, if you will, on how to get the signal through. Does that make sense? No? Yeah. So there's a lot of parameters, what you need to know. The headline here is instrumented, interconnected, and intelligence, the 3 I's. Those are what we're trying to do. We want to connect it through instrumentation. Like your robots, you have sensors on them. You may monitor the speed of the robot or the direction. You might have GPS. You might have all kinds of different sensors like LiDAR, sensors like radar, sensors like infrared. They might be giving you information, and that information might be distance or speed or direction, that sort of thing. So instrumentated is very important. How we instrument anything, whether it be a robot or a baby, is all the same thing to me. Interconnected, we have to connect all these things together. And we do that with RF, with radio frequency, we do it with fiber, we do all kinds of different media, and then we bring it all together into one common shared stream. And then intelligence is effectively artificial intelligence, we could say, but it doesn't need to be. It could be analytics, or it could be just some basic algorithms doing functions. So, and we bring together a very wide variety of technology. So when we do this on big systems, big robots, we get a lot of data, like the babies, 1,000 pieces of data per second. And we have to understand that and analyze that. But let me go back to the baby for a second. A nurse, a 20-year veteran nurse at a hospital in a neonatal ward could monitor the machines, and in 24 to 36 hours, that nurse, because of their vast experience, could tell if the baby's getting a cold. That's very bad because a preborn baby is very fragile, so a cold could be life and death. So those nurses are so expert, they read the 16 machines and they can understand what's going on because of their experience. It takes them 24 to 36 hours. With AI, we can do it in 1 hour. We can diagnose the cold in 1 hour. If we can get ahead of the problem, we can solve the problem before it happens, okay? So it's all about being proactive rather than reactive. Those are 2 key words in robotics for us. And then that means pushing different systems out around. Like we have edge computing now, and we do a lot of technology where we intermix, say, deep learning AI at the cloud with machine learning at the edge in the device, and then we bring those together. Now, I don't bring all the data back. I bring back derived data, a summary of the data. I don't need to bring all the data back. I may log it at the edge and then have it available for maybe 30 days if I need to go and find out what happened. So I could log that data, but I don't necessarily need to transport it. So the architecture of these systems, we use a federated model where we have intelligence at the head end, we have intelligence at the device, and then we intermingle them together. When I say federated, think of the government architecture in Canada. We have the federal government, and they do certain functions like military, and they provide money for healthcare, for instance. But they download that money to the provinces, like Ontario, and then Ontario administrates the healthcare. But in a community like Stony Creek, we might have doctors' offices, we might have clinics, we might have different things. So it's a very layered structure, and each structure has different functionality, but they integrate upstream and downstream with each other and share information. Like the pharmacies may get your prescription, or the doctor may electronically send your prescription to the pharmacy. So you just walk up to the pharmacist and you give your name and show some identification, you get your prescription. So it's that kind of integration. How is that happening? It's happening over RF. It's happening over communication. It might be fiber optics, again, it might be wireless, could be Wi-Fi, it could be all kinds of things. In Canada, we have a number of frequency bands, and there's quite a wide variety of them. And there's a basic snapshot of the bands. Normally, we work in UHF, VHF, very low frequency, and ultra high frequency, and that's what we do like all the time. But I work up into 40 gigs, 60 gigs, way up high for some of my robotics. Why? Because I have 1,000 megabit per second connections over wireless. So very high speed data. The government of Canada produces this map. You can order these online from ISED, the Innovation, Science and Economic Development Division, and they'll send you, it's about a 2-foot by 3-foot map of all the spectrum. But in this table, I know you can't see it very well, but in this table it tells you what you can do in every frequency. Very functional map to know. You need to understand what you can do where. We just can't do everything everywhere. So some frequencies are meant for voice, like police radio or aviation radio. Other frequencies are meant for broadcasting TV or radio, AM and FM. Other frequencies are meant for telemetry or electronic vehicles, have the Tesla so it doesn't crash into the walls or other cars. So we have all these frequencies assigned by the government. When we think about data, we look at 4 chief characteristics of data. We look at how much data there is, the volume of data, because I need to figure out how I'm going to carry that volume. If it's a huge volume, then I have to have a huge connection for it. We look at the velocity of the data, or the variability of the data, and we understand what it can do, what it can't do. And then the variety of the data, we might have a whole bunch of disparate parts. Think about the eBaby I mentioned, my first project. That eBaby was getting blood pressure, heart rate, oxidization, all kinds of different data from different machines. And they were all different. They were not aligned to each other. So it was a big variety of data. We might, in your case, you're using cameras. You might be using radar or LiDAR or different sensors, all different types of data that might be pulling up. And then also I'll say, we need to characterize the types of data that we have in order to understand how we're going to carry them and transport them. That's the very important point. When we are connected, we start out, we have just basic data. And data is it's pretty useless. It's a lot of volume, but it doesn't tell us a lot. Data becomes or evolves into information. And then from information, we go and it becomes knowledge. These 3 things, data, information, knowledge, are all reactive things. They're things we react to. But as we move up the scale, we get insights and wisdom. These are proactive data. When I get ahead of the data, I get to know what's going to happen before it happens. I can now solve problems like electric vehicles or automation, or have an airplane land itself, because I know I can predict what's going to happen. So it's getting ahead of the data. That happens, the more we get, the more connectivity we need to have that happen. And then the more connectivity we have, the more understanding we have. They all go hand in hand. Here's a typical architecture I've been using, and I've used this on 50 projects, all different types of projects. All would be classed as robotic projects, and but we'll have a head end that monitors. I'll show you some live pictures of a real head end in a minute. And we have devices out in the field, and the field could be anything from a home, in the home. I'll give you an example. Some people with diabetes now wear monitors that attach to their arm for a month at a time. They talk with Bluetooth at 2.5 gigahertz to a monitoring station that can talk to your doctor and let the doctor know about how you're doing. There's also people that have defibrillators built in to control the pace of their heart. some of those defibrillators can give you a shock, electric shock. If your heart goes off, they can trigger that. Well, you don't want that happening automatically. So you want that data to go out to a doctor, and the doctor say, okay, hit the defib, and they'll bring you back without even anyone being in attendance. That exists today here in Ontario. So it's quite interesting, but we need people to be involved in the process, or it will go very wrong. We won't say much more than that. But this architecture, I use it in mines, I use it in electric vehicles, I've used it everywhere. I went to Toyota City in Japan one time, and we were working on the next generation of electric vehicles. We worked on the General Motors Bolt and Volt, and they're all using this type of architecture as well. All the drones we're working on right now are using this architecture. We're controlling drones in Edmonton from Toronto, and the AI is watching them right now. I'm doing a project in a place called Olds, Alberta right now, where we're setting up radar to monitor drones in the sky for firefighting. So there's some very interesting implications, but it's all about integrating systems together and having them work in harmony. So when we look at modulation, a very basic form of modulation is called spread spectrum. This was invented by a woman, a Hollywood star named Hedy Lamarr, and she held the patent, which she donated. Why this spread spectrum is in every one of your phones today. She invented it in World War II. And so it's very old technology. How did she invent it? A lot of our ideas come from looking at one piece of technology and leveraging that technology across. In the 40s, Hedy Lamarr would sing, and they had pianos, but they were called player pianos. You probably have never seen one, but they used paper, and on the paper they had holes punched in, and the holes matched the 88 keys of the piano, and the paper rolled by. And so whenever a hole was there, it would press whatever key on the piano, and the piano would play by itself, okay? So Hedy Lamarr looked at that paper, and what did she see? She saw the 88 rows of holes. She saw it moving. What does that mean? She had space and time, right? The space and time connection, and then she put up her radio frequency system, which took the same signal many times and replicated it. So if it was blocked once, it would get through another time because there's many copies of it going in parallel. And she used that model to create spread spectrum. And it's in every one of your smartphones today. But she donated the patent for free. And in 1988, before she passed away, she won the Scientist of the Year award in the United States. And that patent, she held, I think, over 90 patents. She was a genius woman. But she was also in some of the old movies like Samson and Delilah, and she was billed as the most beautiful woman in the world. And she probably was at the time. Nowadays, we use different forms of modulation. We use QAM, I call it QAM, which is that grid work that you see there. And we put up many pieces of data simultaneously. We run a high order modulation now. And QAM means quadrature, meaning 4 quadrants. Amplitude modulation. What's that amplitude modulation mean to you? AM radio. So we're using technology we're mixing technologies again, using the old to make the new. With QAM, you need 2 bits to make a byte. 2 symbols to make a bit. So in this one, it's 64 symbols. We can get about 8 bits of information on every cycle or phase that goes through. So there's enough about the technology. Let's put it into practical sense and use some examples. So here's a project I did at outside of Kamloops, Alberta. 1 hour outside of Kamloops. Kamloops, if you know, is in the Rocky Mountains. Actually, the Coastal Mountains, it's called, that range there. And where this mine is, it's called Highland Valley Copper Mine. There's nothing there. There's no cellular. There's nothing. 0 signals. Now, at this place, it's so quiet, it hurt my ears. It was so quiet. There's no noise. I live in Toronto. I hear noise all the time. My ears are used to noise, car noise, truck noise, whatever. In Highland Creek, there's no noise. It's so strange. It was like a ringing in my ears, like a vacuum. So there's nothing there. There's no frequencies. What is there are bears, elk, wolves, bobcats, cougars. There's a lot of things that can kill you. So it's an interesting place to go. But it's a mine that's quite gigantic. And it's just amazing. Now, there's two types of automation in mining. We automate the software and the systems, and then we automate the technology, the vehicles, the mining vehicles. So think of them like EVs today, but only we're automating dumps. We call them, they're dump trucks or haul trucks, haulage trucks. But we automate these dump trucks. We automate the dozers. We automate the shovels. We automate the whole factory. What's a factory? Well, we take the rock and turn it into minerals. We separate the copper away. And we get other minerals too. We get gold and all sorts of other byproducts. A typical mine, whether it's a nickel mine in Inco or copper mine in Kamloops, they don't just make one thing, even though they call it a nickel mine or a copper mine. That's the principal ore. But typically you'll get 8, 10, 11 different ore types out of there. So some of the copper mines can produce more gold than the biggest gold mines. So it's quite amazing. Now, here, if you look at it, and let's compare it to your robotics here at Team 2056, okay? What's the differences? The mines are in remote places. You play in gymnasiums. I've gone to your events. I've been to the, what's it called now, the Hershey Center? No, it's Paramount Fine Foods Center. It used to be the Hershey Center. I've been to McMaster. I've watched the teams compete, all the teams. And so scale of location is very different. The mines are underground or in pits, and it's a very hostile environment. Winter, they're outside or underground. I've been in a mine, I've been 2 miles below the earth, and I've been in a foot of water. And you're walking around, every moment you're walking around, you're in water. It's terrible. Your feet are freezing cold. It's not fun. So you're in a very hostile environment. There's other things, the location. The mine that I'm talking about now was 30 miles by 30 miles, 900 square kilometers. You guys operate in a gymnasium, So now to provide RF coverage on a footprint that big takes some very different techniques. It's 6,000 feet above sea level. That starts to affect performance of equipment like motors. It's a mile high. It's several kilometers high, right? So almost 2 kilometers above sea level. That affects motors in the way they operate, gas motors in particular. The air to gas ratio, the barometric pressure is different. So we have to take that into account. And in this case, it's in a semi-desert. So it's very, very dry. Even in winter, you get shock and static on everything. So you got to insulate everything from static shocks. And again, the animals that are there to try and eat you. But still, I think Toronto traffic can be worse than the mine site here. And no sound, I mentioned. So in this graphic, you can see this is the process of a mine, step by step. I tried to make a graphic. It's hard to see, I know, especially on the stream. But I'll leave the slide deck behind. You can have the slides. But what you get here is you can see that we use dynamite. And every morning at 11 o'clock, they blow up dynamite, and everybody has to get out of the way. And then sirens go off, and they blow up stuff. And then they dig up the rock that got blown up and load it into dump trucks. Dump trucks take it over to the conveyor belt. Dozers push it onto the belt or into the supply. And the belt takes it into the processing plant. And then we process it. So a mine is a very connected thing. And we'll use fiber optics. I worked on one mine in Chile, and the conveyor belt is the longest one in the world. It was several miles long, many kilometers. And you can see it from space. It's so big. That mine, they call it Colossus, is the biggest copper mine in the world. 10% of the world's copper comes out of that one hole. And all the copper goes to China to make circuit boards so they can make smartphones or tablets or Game Boys or whatever you want. So mining is very important, but their product, and out of that mine in Chile, more gold comes out of there than the Red Lake gold mine in Ontario, which is the biggest in Canada. So there's my toy. That's what we operate on. That's a Caterpillar 793F, and we automate that thing to the ends. You wouldn't believe. We even have magnets inside the cylinders. So if the piston is rubbing against the wall of the cylinder, we call it throwing metal. If it's stripping or shaving the cylinder, the metal particles get in the oil, and then when they flow down, they stick to the magnet. Those magnets detect the metal particles and give us an alarm and tell us that cylinder number 3 is throwing metal. All the cylinders in these Caterpillars we can remove individually. We don't have to do them all. We don't have to lift the whole block together. They're all individual. We call them cans, but we pull them out individually. But if you look at the people, the size of the people, you can see how big that thing really is. It's about 300,000 pounds empty and about 800,000 pounds when it's full of ore. So if that thing runs over, you're in big trouble. So health and safety is a really big concern at any mine. So you have to wear hard hats and boots and vests, and you would expect that. But we're now doing something a little different because of the impact of what these huge, heavy vehicles can do. You have no chance. There's zero chance of survival. And here are some vehicles that have been run over that I've snapped photos of over the years. And what we're doing now is we're instrumenting the workers. We're putting sensors in their overalls, and we're measuring how many steps they take, what their gait of their step is like. Are they getting tired? They work 12-hour shifts. They get tired. Most accidents happen in the last 2 hours of the shift because they get tired. And so now we're measuring perspiration, heart rate, blood pressure, everything. It's all in the suit. So we can monitor, we instrument the workers. And now we put GPS on the workers. We know where the workers are compared to the equipment. So we can stop the equipment if it's coming near a worker, okay? When you look at that mine was 3 mines that we integrated, or the company Teck Resources owns the mine, and they integrated 3 mines into one. It's been mining there since 1886, a long, long time. They've been pulling ore. So that's the biggest open pit mine in Canada, okay? And there's a picture from a drone shot of the mine. And that mine, if you know British Columbia at all, if you looked at it, you can see it's up near Kamloops at the top there. And that ore body stretches all the way down to the US border. That's maybe a 4-hour drive to get from top to bottom. That's a big area, okay? And then the size of the pit is huge. It's all layered or terraced. Each of those layers are 45 feet because the dump trucks drive on them like roads. And it's like the bunny hills on a ski resort. You can corkscrew all the way out to the top to get out of the mine. So even if you look at those layers in the mine, you got to appreciate the scale of what you're looking at here. And again, that is the biggest open pit in Canada. Now, when we look at the Caterpillar 793F, there's some specifics on it. It's over 2,000 horsepower on that thing, a little more than a Tesla, okay? And we pull all that telemetry out of the cylinders and all the fuel that it's carrying, and we take the driver. There's no drivers in these trucks. The trucks all operate independently. We did a pilot with 8 start, and now we've done all their mines. They're all automated. But they don't have to stop for lunch. They don't have to stop for breaks. So they're getting way more productivity out of the vehicles in a day. A couple hours more productivity on a 12-hour shift. They're getting at least 2 hours more productivity. And the utilization, and they can control the speed. We run the vehicles when they're driving at about 43 kilometers an hour. So, and they're all geared, and they can to go up the ramps and the hills. It's very difficult for them when they're fully loaded. You can imagine. But we can monitor them precisely. And we use all kinds of different technology on them. We create a bubble around the truck. We know everything within that bubble. And we use LiDAR, we use radar, we use FLISR, forward-looking infrared, we use video cameras, and all kinds of different sensors. What do you think the biggest problem is that we have? Any thoughts? It's dirty. Got to keep stopping and cleaning the lenses on the cameras and such so they can see. The dust kicks up big time. So they have trucks now, autonomous trucks, that just put water down on the road so that it's like a sprinkler truck like you see in construction to keep the dust in. Yes?
Would there be like any way to like program it to like clean itself?
Oh, sure. You can do that, but then did it work or is it better? We have automated wipers on many systems, and we have sensors to detect the dust on the lens. Yeah, so we do that already. I know that, again, this will be hard to read, but there's on that truck, this is all the things we did to it. So on a vehicle, even in your cars, there's something called an OBD2 port, onboard diagnostics version 2. And we plug into that and we can pull all the telemetry. So we know the speed it's going, we know the RPM, we know the temperature of the engine, if it's overheating. We know the transmission. We can pull all the data out of the transmission, everything out of there. We can pull information out of the tires. Those tires are about 5,000 Canadian a piece. There's 6 tires on each dump, and we have 2 sets of tires a year. So it's about $60,000 a year in tires on those things. They change them every 6 months. They don't get a lot of use out of the tires because of the loads, the weight, and the terrain. The roads are changing every week. One week there'll be a road there, and the next week it's a hole. So we hire video game people that make video games, to come in and create the maps every week. They're the best. We hire them out of the University of British Columbia, which has got a really good gaming program there. And they help us with that, to do that. And then there's all different types of equipment in a mine. So I've been showing you the dumps because they're kind of cool. They're big. I like dump trucks. But there's all kinds of shovels and dozers and all different machinery. And there's over 600 pieces of equipment. But we instrument the work trucks, the Ford F-150 pickup trucks. We instrument the people. So we'll have a lot, maybe 600 devices all in play in the mine at the same time. And then we do even more. We create this bubble around the vehicle so that the vehicle's got a multi-dimensional feel for what's around it. It knows when people are there. It knows when pickup trucks are there and how far they are. It knows all this telemetry, and it knows what to do. It does all this, and it reports back through RF, through radio frequency. Again, the truck is operating independently, but it's communicating to the head end. We call it the head end, which I'll show you now. And it's a whole bunch of screens, and it shows maps, and these maps have to be updated every week because the mine's changing every week. And we have a command and control center with fantastic screens and displays and all kinds of computers that are monitoring what's going on. And we have some very complicated rules that have been programmed in. For example, if the truck doesn't communicate within 10 milliseconds, we tell it immediately, cut your speed by 50%, slow down. So if we lose communication is that important that we're going to hit something. And when you hit something, those trucks are $1 million collisions on each truck. And then you lose productivity. It's $100,000 of revenue for every dump truck load of ore. So if that truck goes out of service, if it's out of service for 2 hours and does 2 loads per hour, is 4 loads, is $400,000 in lost revenue. Okay? So it's not just the collision and fix the dump, it's the lost revenue from the dump not working. So we monitor all of that, and we make sure it all works really well. And AI is in the dump truck. AI is monitoring in the cloud. AI in other cities. But the data center is in Kamloops. It's an hour drive away to the data center. So, and the operators can be anywhere. They could be on the other side of the world. Doesn't matter where they are. So there's a wide shot I took. This is actually at the mine site because we were doing the pilot. So we built everything at one place. We built a data center there too. But today we don't do that. The data center is in Calgary today. And so it's in a different province. The mine's in British Columbia, right? So all very different. But we use this, we can speed with fiber optics. We can get that traffic through very quickly. And then we're looking at trends and patterns and anomalies and statistical outliers. So AI is heavily built on statistics. If you understand stats, you'll understand AI. If you understand AI, you can understand RF. You can't have AI, you can't have autonomous vehicles without RF. We need it all the time. So here's a crude, I tried to show you everything on the truck that we put. We did redundancy. So there's 2 GPS eggs. We put them up high. So number one, they could see the satellites. And number 2, they wouldn't get hit by anything, by the shovels or anything else. So we got them out of harm's way by putting them, everything had to be thought out very carefully where you're going to put it. So, and we use differential GPS. I don't know if you've heard of that. You know GPS, I'm sure. But differential GPS, we send out a second signal from the ground, which we correct the error in the GPS. The GPS has what's called a dither. And in a normal GPS system that would be in your phone, it'll be accurate within 10 meters, 30 feet. We need much more better accuracy because 2 trucks could hit each other if they pass on a road. So we use differential GPS, which corrects for the dither, and then we bring it down to sub 1 meter resolution. But really, we're down to 1 centimeter resolution, 1 centimeter accuracy on GPS. But that's a very specialized system that we have to make the GPS more accurate. Yep.
So how come, like, why normal GPSs, why do they have that, like, inaccuracy? It's just because they're not, like, advanced?
Yeah, because it's coming from outer space. They're 500 miles above the Earth. So it's just a natural error of that distance. But 10 meters is pretty good, you know, if you think it out. So what we do is we send a correction signal from the ground, which tells the GPS use -8 meters or -6 meters. As it moves around the yard, it's going to vary. And again, the yard is 30 meters or 30 miles by 30 miles. So LIDAR, do you all know what LIDAR is? Ever heard that term before? LIDAR is a type, think of it like radar, but it's light and distance ranging. That's what LIDAR is an acronym for, light and distance ranging. And it allows us to detect distance. It allows us to detect shapes as well. So it's very good at creating shapes. And we use video cameras, which also we can do the same thing. But LIDAR gives us a three-dimensionality to the shape of something. So we can see it's a person walking. We can even detect which way they're walking because the camera will see the face. And we know they're going to be walking theoretically forward if we see the face, right? Pardon my spelling error here, but forward-looking sensors like infrared thermal imaging we use as well. Laser, radar, all sorts of things. FLIR is forward-looking infrared. That's what the acronym means. And then we have lights on the trucks, and the lights give the operators, the humans around them, so they know they won't approach the truck if it's in autonomous mode. So the command center, they call on the two-way radio and say, I'm at truck number 123, please take it out of autonomous mode. And then the light will change on there. So tell the humans that truck's safe to walk up to. So we have 3 different color codes for semi-autonomous, fully autonomous, or out of manual mode, so to speak. Now, how do we do that? When you have 900 square miles, how do you do that? So we created something called a COW, C-O-W, a cell on wheels. And we have them where they're all portable. So here's some cows that we built, and they have solar panels. There's no electricity out there, so we have to make our own electricity. We use solar panels, and we have telescopic antennas that mount, they go up. So we park the cow someplace strategic, because again, the mine's changing every week. So we have to move the cows around, and we get sunlight with them. And pardon this shot, but I took it out of the pickup truck I was driving while I was driving. So there's a cow with the mast up, and you can see the radio gear on the top. So we move those around, and then we use microwave to beam them back to the control center. So again, latency is very critical because the truck only has 10 milliseconds. Do you understand milliseconds? Like a second divided by 1,000. So it's 10 1,000ths of a second. You blink your eyes at about 300 milliseconds. Okay? When you stomp your foot on the brake on the car, it's around 250 milliseconds if you're really good. So we have 10 and 20 milliseconds. At 20 milliseconds, all vehicles stop. If one vehicle stops communicating for 20 milliseconds, everybody freezes. Everything stops because something's wrong, right? So it's very critical. Now, what do we do with all the ore? We get in the dump trucks. Now we load it in the conveyor. But those 3 domes are like, they'll hold Iverwind Stadium 3 times in each dome. They're gigantic. Gigantic. I'll show you pictures inside in a minute. But the dump trucks come and dump the ore into a scoop system, which draws it into the conveyor belt. Okay, and the ore is all just been blown up and shoveled, and it's big rocks and everything, right? And then it goes in along the conveyor belt. It goes into these spinning rock crushing machines that make the big ore come down into little pebbles. Okay, so we grind it all down, and they have 3 of these machines there, and they crush the ore by spinning them, and they're always going, but they bring it down to 0.155 inches. Now, the reason I'm using inches and jumping metric, just so you know, we live in metric world, but U.S. is still in imperial. They still use inches and feet, and all this equipment comes out of the U.S. So I have to jump back and forth all the time. It's very helpful. When I do drones, we have very confusing. We buy our fuel in liters, but the airplane will take gallons, so we have to convert that. Our airspeed's in knots, nautical miles. Our altitude's in feet, right? We also use kilometers and all kinds of different parameters. So you have to jump between 3 systems when we do aviation drones. Okay, so very complicated, and you have to do a lot of math in your head, but it gets easy after a while. And here, the little pebbles, they now go into a bath, a toxic chemical bath, which breaks up the ores apart, and it allows them to separate the gold and the copper from the rock. And it goes through what's called a slurry. And then it extracts all the elements, okay? All that's automated. You don't see a robot there, but everything is automated. Everything has controls on it. We have cameras looking at the size of the stones, measuring them as they go by. So because if we have too big of stones, there's something wrong upstream, and we slow down the conveyor belt. So we can throttle the conveyor belt speed based on the size of the pebbles going through it. Okay, and there you can see the whole slurry system all under that dome roof. Gigantic, like football fields large. And then out of it, it comes to what they call tailing ponds. Tailings are the crud that has no value. But in the old days, they used to just pour it into a pond, and it was toxic. It would kill everything, all the birds, because it was full of acids and ammonias. And nowadays, they have to clean it up. And now they're so clean that fish can live in these ponds, right? And it's now a very different environment. We have to be clean. We have to be safe. We have to do things differently today than we normally do. So that's the end of it, unless you have any questions. And I'll end there. There's my phone number and my email, and anyone's welcome to contact me at any time. Just identify yourself as First Robotics Canada, and let me know what your question is, and I'll be happy to answer it or send you information. What I didn't put up here, and I should have, I have a blog site, and all of these stories are written up. There's over 400 articles that have been published on different projects. So you'll find stuff on drones, you'll find stuff on mining, you'll find stuff on EVs, electric vehicles from Toyota City in Japan. You'll find a whole bunch of different things that might interest you. And that blog site is called vividcomm.com. So it's vividcomm.com. So don't forget 2 M's at the end. If you only do 1 M, you're going to get a very bad site that has nothing to do with me. So, but 2 M's and you'll get the blog site. And all the articles are in order. You can search on them. You can do all sorts of stuff. So there's all the eBaby. After I did the eBaby, I did the Tour de France. And we instrumented the bicycle riders on the Tour de France. That article's up there. That was very interesting. After that, we did Formula One. So if you like cars, if you like this stuff, then it's good for you to have a look at. Okay? Yes.
What would you say is like the future of autonomous technology and its like effects on like jobs and like working?
Well, there's a lot of people are worried about that. Well, every time we have a new technology come out, and I've seen lots of them, I started in the analog world. That's all gone. So, but we have new jobs that have come forward since then. Okay, so one of the statements I'd say is lifelong learning. You got to be a lifelong learner. Where your parents might have had one job for their whole life, that doesn't exist anymore, and it's too boring anyway. It's better to have more jobs. But things are changing. The jobs you'll have when you graduate university don't even exist today. So that's how fast change is coming. So I'm going to say to you, to answer your question, that there will be new jobs and new roles, but you have to be retrained and constant. You got to get into an attitude of constant retraining. I do. Does that answer your question? Good. Okay. Okay. I think we're all done. I don't know how you turn that off, but.
I have no idea what the Wi-Fi password is.
Bro, is that your work off?